Hello everyone. In this video, I'll be giving an introduction to fluid mechanics, advised by Professor Imad Al-Mahmoud. Let us begin. The best way to understand something is to examine its fundamentals. For example, if you want to determine the properties of an object, you will have to know what it's made of, what elements and compounds. Then you can predict some of its properties theoretically rather than experimentally, which costs time and resources. So, what are the fundamentals of fluid mechanics? Where do all the equations come from? Please pause the video and think about the answer for a moment before continuing. I hope you gave it a fair shot. The answer is simply conservation of energy. So, everything we will be doing can be summed up in the following procedure. 1. Analyze the energies present in the system. 2. Express the energies mathematically. 3. Apply conservation of energy. I will explain the procedure step by step, but before that, let's talk about assumptions. Before we start studying fluid mechanics, we will set several assumptions. We do that to make our study easier. Think of it like driving a car. Before you can start driving anywhere, you must learn how to drive in a safe environment with no traffic. Similarly, we will use several assumptions which are essentially restrictions that will make our learning process safer and easier. The first assumption is that the fluid is non-viscous. In other words, there is no friction between the fluid and the surroundings, or attraction between the molecules of the fluid. The second assumption is that the flow is steady, which means that the velocity of the fluid is the same at each point. The third assumption is that the density of the fluid is constant. The fourth assumption is that no whirlpools will form in the fluid, as whirlpools will affect the speed of the fluid and the rate of flow, and will completely ruin your calculations. It's also very hard to predict them. Therefore, we will restrict our calculations to scenarios where they don't form. Energies found in a fluid mechanical system. Many types of energies can be found in such systems. However, in our level, we are only interested in the following. 1. Potential energy due to pressure. 2. Potential energy due to conservative forces. 3. Kinetic energy. For pressure, we have internal pressure and external pressure. For conservative forces, we will only study one type, which is force of gravity. Finally, we have two scenarios for kinetic energy. First is the kinetic energy of a moving fluid. Second is the kinetic energy of an object moving through a fluid. However, the second case can be solved using simple dynamics, by taking the fluid resistance the same way we take air resistance or friction. Therefore, this case is irrelevant for us. Let's now talk about the mathematical expressions. Don't worry, it's easy and straightforward. For pressure, it's not possible to write one mathematical expression that will always work, because each system is different. This is better explained in examples, as you will shortly see. For now, it's sufficient to say that the pressure of a fluid equals its density times gravity acceleration times height. For potential energy due to gravity, it is equal to the mass of the object times gravity acceleration times height. However, if we are talking about a fluid instead of an object, we can't use mass, since the center of mass is constantly changing. Therefore, we will divide the equation by volume to replace mass by density, which is taken to be constant. As for kinetic energy, it is equal to half the mass of an object times the square of its velocity. And again, we can't use mass here, so we divide the equation by volume. Now it's finally time to apply conservation of energy. We simply set the addition of each expression of energy to be constant. However, before we accept this equation to be true, let's analyze it a bit. First, we have pressure. Then we have potential energy divided by volume. Then we have the kinetic energy divided by volume. Is that really a conservation of energy statement? Is pressure a type of energy? Are these two types of energies? The trick here is knowing that pressure is indeed a type of energy. In fact, it is an energy divided by volume, just like we divided potential and kinetic energy by volume. Therefore, this expression can be rewritten as the following one. Then we can multiply it by volume to get nothing but an addition of energies. Now that we know that this equation is a valid statement of conservation of energy, we can drop the second one because we don't need it. Proving that pressure is a type of energy divided by volume was not an easy thing to do, and the guy who managed to prove it got this equation named after him. Can you guess his name? It's Bernoulli, and this right here is Bernoulli's equation. Now that we have established our conceptual and mathematical basis, we can begin solving examples to see how this plays out. So then, let's take a look at this example. It reads, a crown weighs 7.84 Newton in air and 6.84 Newton in water. Is the crown made of pure gold, neglecting air pressure? And the density of gold is given to us. Let's follow the procedure. 1. Analyze the energies. Looking at the first diagram, we can see that the only energy present is the potential energy due to gravity. Looking at the second diagram, we can see that we also have potential energy due to gravity, but now we also have potential energy due to pressure. We can see that nothing is moving, therefore the kinetic energy is 0. 2. Express the energies mathematically. Potential energy due to gravity equals mass times gravity acceleration times height. And since we are talking about an object rather than a liquid, there is no need to divide by volume. Potential energy due to pressure equals the density of the liquid times gravity acceleration times height. And as I explained previously, pressure is a type of energy divided by volume. So we multiply the pressure by volume to get energy. Note that this expression without height is called buoyancy force. However, I prefer looking at the whole picture by considering energies instead of forces. 3. Apply conservation of energy by simply setting the energy in air equal to the energy in water. Let's substitute our mathematical expressions. For energy when the crown is in air, it is equal to the potential energy due to gravity. For when the crown is in water, the energy is equal to the addition of potential energy due to gravity and potential energy due to pressure. Let's substitute our numbers. We can see that each term has height, so we can simplify the equation by dividing into height. Knowing that the volume of the crown is equal to its mass divided by its density, we can simplify the equation even more. We know that mass times gravity acceleration equals weight, which is given to us in the question. Now, all that's left is some algebra. We subtract 6.84 from both sides. Then, we multiply by the density of the crown. We can see that the density of the crown is much lower than the density of gold. Therefore, the crown is not made of pure gold. This concludes the video. I hope it was informative. If you have any further questions, please leave a comment. Take care, be safe.